All right. Well, last time we finished up talking about vector spaces, and we had the one example while we were talking about vector spaces that, let me flip back over to it real quick. Where we have a subset, we had a subset of a vector space. We already know that for any m and any n, m by n matrices form a vector space under addition and under scalar multiplication. We had a subset here of that vector space that had a particular form. There was some particular property that that subset had, or membership property, I guess I should say, that subset had. And we said that basically we only need to worry about whether or not it was closed under addition and closed under scalar multiplication to check whether or not it was actually a vector space, because it already inherits all the other properties from the bigger vector space, right? We already know that we've got a nice, well-defined ordinary addition, ordinary scalar multiplication in this one, but it's already been checked that those properties behave nicely with respect to the vector space axioms. So really all we needed to do was check, hey, do I really land back in here again when I add things or multiply by a scalar? Because, pardon me, because I already know that the addition's commutative. I don't have to check it again. I already know the addition's associative. I don't have to check it again because it works in the bigger set, so it will work in the smaller set automatically. Okay. Likewise with the distributive axioms. And then again, since we have the vector space properties, we know that, for instance, and we wrote these down at the end of class last time, when I do 0 times any vector, I get the 0 vector. So if the set is closed under scalar multiplication, I know that I have the 0 vector in my subset if it's already closed. We know that if I do -1 times a vector, I get its additive inverse. If it's closed under scalar multiplication, I get that it has inverses as well in the subset. So it boils things down when we have the subset. If we want to check if a subset is in fact a vector space itself, it boils things down to just having to check those two axioms. So to that end, I realized I didn't kind of have something to should notes. I saw DeMarcus looking for things. Like, I didn't hand out who should notes. So that's what our discussion today is going to be, talking about subspaces of a vector space. So let me flip back over to that notepad here. All right. So what do we mean by a subspace? So we're going to start with a vector space V. So again, when we say that statement, we say a lot of things. Okay. When I say something is a vector space, I know it has objects in it. Okay. Remember, it had to be a non-empty set to be a vector space. I know we have an addition that is defined. I know we have a scalar multiplication that is defined, and all 10 of those axioms are satisfied with respect to those two operations. Okay, so when we just say the words vector space, there's a lot of stuff going on in that statement. Those two. Okay. All right. So we have the vector space. We've got a non-empty subset of the vector space. Then the W here is going to be a subspace if W is a vector space itself under the same addition and scalar multiplication as V. Okay. Nothing is changing. All we're doing is restricting where we're looking. Okay? That's all we're doing. We're not changing anything else. We already have an addition defined. We already have a scalar multiplication defined. And we know those behave nicely, again, with respect to the axioms. None of that is changing. All we're doing doing is putting some blinders on. Okay? If I make the restriction and put some blinders on, do I get the exact same things satisfied? And it becomes a vector space itself. Why might we care about such things? Well, we've already talked about, we've already talked about how we can write solutions to systems of linear equations as, it's been a little bit ago, but if you have the set of equations AX equals B, for example, we said that we could write this, if it had a solution, we could write it as a particular solution plus something that was a solution to the homogeneous system. And remember, this was, if it had infinitely many solutions, this was the infinitely many part, right? It turns out that these solutions form a subspace. When you look at all the set of all the solutions to the homogeneous system of equations, you get a subspace of, if A is m by n, it would be a subspace of Rn. Okay. I know I talk a lot about differential equations in here. And some of you may not have had differential equations or are currently in differential equations. But when you solve that differential equations, you typically get an arbitrary constant in there, right? Or maybe a couple of arbitrary constants depending on what you're solving. But what that means is that you get all the solutions are in terms of a couple of functions, and then you generate all of the possible solutions out of those. That forms a subspace of whatever function space you're in. Is it continuous functions, or is it differential functions, or those kinds of things? So a lot of the stuff that we're doing with subspaces, again, goes back to how we can describe systems of linear equations. That's the whole point. Okay. All right. Going back a bit and just start learning, or just start trying to do some introductory problems here. Let's look at this particular example. We've got our vector space is Euclidean three-dimensional space, R3. Okay. We know exactly what vector addition looks like in R3, right? How do you add two vectors in R3? Add components. Good. It's add component-wise. We know what scalar multiplication is in R3. How do we do that? Yeah, multiply the scalar times every component, right? So that's exactly what we're going to do in this set, right? The only thing that this set says is that we're going to restrict our focus here. We're going to take all of the vectors that have the third component being the sum of the first two. That's all we're doing. Now, for those of you who have had Calc 3, if I do this graphically, what kind of a shape do I get if I graph this equation? What do I get? You recognize that as an equation of something. It's not a hard thing. Starts with the letter P. That's a plane. It's a plane. Okay? It is a plane. So you have this plane that goes through the origin, right? The point 0, 0, 0 satisfies that equation, doesn't it? Okay. Goes through the origin. Why is that important, by the way? Why is it important that it goes through the origin? What vector do we need to make sure is in our subspace? To make sure that what is it? The zero vector is going to have to be in there, right? Remember again, one of the arguments that we made was that if this is closed under scalar multiplication, then 0 times the vector has to be back in there again, and we know that 0 times the vector has to be the zero vector in the space. Okay? So it's important that the plane, in this case, it's the equation of the plane, goes through the origin. If it doesn't go through the origin, it's not going to be a subspace, because the zero vector won't be in there. Okay. All right. So if we want, pardon me, if we want to show that this really is a vector space, we already know, I'm just going to rewrite what we wrote last time. We already know that axioms 2, 3, and 7 through 10 hold in W because they hold in V. And every vector in W is a vector in V. Where V in this case is our R3. Okay. I don't need to recheck the axioms again, right? We know that for any Euclidean vectors, I know that I can add them in either order. I know I can regroup them. I know the scalars distribute appropriately and all that good stuff. We already know that for free. I don't have to recheck it because I know it works for every single vector in V, right? So the idea here is that if we can show that axioms 1 and 4, not 1 and 4, axioms 1 and 6 hold, and just to remind, those are the closure axioms hold, then axioms 4 and 5 must also be true. And remember, the idea behind this is that if I know this one, if I know that it's closed under scalar multiplication, that was what number 6 was, I know that 0 times a vector in W, that has to be the 0 vector in V, which I'll write it that way just to emphasize that it's the 0 vector of V, has to be back in W again, right? If it's closed, if I know that when I do a scalar times a vector from W, it lands back in W again. That's what closure means. If I know that it's closed under scalar multiplication, then 0 times any vector has to be back in there again. But in V, when we do 0 times W, what do we end up with? The 0 vector. We proved that, right? Okay. So the 0 vector from V has to be back in W again, which means I get a 0 vector for free because it's closed under scalar multiplication. And we know that -1 times W has to be the negative of W in V because it works in V, but since it's closed under scalar multiplication, that has to be back in W again. So again, I don't have to recheck 4 and 5 either. I get them for free. Okay? So the idea here is that all we need to show something is a subspace is that it's closed under the operations, and then we're done. It's a vector space itself, so it's a subspace of the bigger one. Yes. I already know that this is a vector space. We're given that it's a vector space. I get that these are whole because I know that the big space they already hold. If I tell you it's a vector space, those 10 axioms have to hold for the big space automatically. That's what it says. That was what it means to be a vector space. All of those things are satisfied. Okay. This smaller set is a piece of V, right? So every vector that's in W is also in V, right? Okay. So if I put those in those axioms, if I take any two things from W and add them together, the reverse also has to work because it has to work in V. So I get it for free. If I take 3 of them and look at my regrouping, I can regroup any way I want because it had to work in V because they are vectors in V themselves. Okay. The only thing I need to worry about is whether or not I land back in the right spot for subspace. Because the other ones we get for free because it holds for the bigger space, so it has to hold for the smaller set. That's why. Okay. Will I give you those? No, you have to know those. No, you have to know the 10 axioms. Okay. All right. So let's go through what we would have to show here. All right. So we're going to start, pardon me. We need to show the closure axiom. So remember, the closure axioms are, if I take two vectors and add them together, I land back in my set again. And if for scalar multiplication is if I take any real number, multiply it by a vector, I land back in the set again. Right? All right, so let's start with, I'll call it W1 is X1, Y1, Z1, and W2 is X2, Y2, Z2. And we're going to say they're both in W, right? What was the defining characteristic for being in W again? I got it back up there at the top of the screen. What's the identifying characteristic for being in W? How do we know that something is in W? Yeah, if I take the third component, it's the sum of the first two, right? So I know that Z1 is X1 plus Y1, right? And Z2 is X2 plus Y2. Now, what happens when we take W1 and add W2? Well, I'm going to get I'll get an X1 plus X2, Y1 plus Y2, Z1 plus Z2, right? That's how we add them, isn't it? Okay. Now, what do I need to show? What do we need to have? If this is going to be back in W again, what has to happen? Yeah, the first two has to add to the second two, right? Okay. So if I take the first two, rearrange, it's just rearranged, right? I took the first one and the second one, added them together. I just rearranged it. They're just real numbers, right? I can do that. What's the first one equal to? The Z1, right? From this property right here. Yeah. And what's the second one equal to? Z2. And isn't that what we wanted to show? Yeah. So W1 plus W2 is back in W. And W is closed under addition. Yeah. Okay. That was axiom 1, right? So again, notice how we did this, and this is how we should start all of these. I start with two vectors in my purported subspace, right? I'm purporting that this really is a subspace, correct? Okay. That's what I'm hoping happens. It really is a subspace. So I'll start with two vectors in there, and then I wrote out what the defining characteristic was for being in there, right? Here's the defining characteristic. Third component is the sum of the first two. Then I added them together because I have to show that it's closed under addition, so I added them together. And then I showed that the sum has that defining characteristic. I looked at the sum of the first two components and showed that it was equal to the third. So that's what it means to be closed. I need to do the exact same thing for scalar multiplication, right? So let's see here. Remember, all of our scalars are going to come from the real numbers here, okay? Let's just take I've already got my W1 defined, so I might as well just use that again. What is C times W1 again? CX1, CY1, CZ1. Now again, I need to if this is going to be a subspace, I need to show that this is back in W again, right? Our defining characteristic for being in W is what? Yeah, the sum of the first two components is the third, right? So I'll take my first two components and add them together, what do you think we might want to do? Pull out the C, good. And then what do we know about x1 plus y1? It equals z1. Is that what we wanted to show? Yeah. So C times W1 is back in W, and W is closed under scalar multiplication. So we showed that it's closed under addition. We showed that it's closed under scalar multiplication. Hence, W is a subspace of V. And our V in this case is R3. So I'll write it as R3. Now remember, we talked before about proving something as a vector space. Proving something as a vector space requires all 10 axioms to be proved, right? Because I need to check that every single axiom is satisfied by however we're defining the addition and the scalar multiplication. For a subspace, we only have to prove 2. So the subspace ones are a little bit easier, right? Hopefully they're a little bit easier. Should be 20%, it will work. All right. We're going to do more, but questions on this one so far? Yes?
What does that mean for the set process for all subspaces?
Say it again.
We follow the same operation.
Well, you have to, yeah, it's the same 2 axioms that you have to prove for anything that you're trying to prove as a subspace. Every subspace, yep. So that's exactly what I'm going to write down now. So our test for when subset is a subspace, okay? So if W is a non-empty subset of V, then W is a subspace of V if and only if W is closed under addition and scalar multiplication. And I'll just say using the same operations as B. Okay, so the proof, we've already kind of talked about the proof, but we'll go ahead and write it down so that we have it all in the same space. Same place. All right, so one of the reasons why I want to kind of talk about the proof here is notice that this is an if and only if statement. So just from a logical standpoint, when you say if and only if, that means that we're going to assume the first part, assume W is a subspace of V, and then prove W is closed under the scale addition and scalar multiplication. But also vice versa. If and only if means the theorem works both ways. So I assume the first part, prove the second part, assume the second part, prove the first part. Okay? So typically in math, when you want to show that you're proving one direction and then the other, you make a little arrow, put parentheses around it. This is just telling the reader. Mathematicians like to talk to the reader a lot. One of the things you'll see in math papers a lot is the proof is left for the reader. So we talk to the reader quite a bit. The reader will notice. I wish I were lying, but that's how they write. How we write, I should say. It's not a they, it's a we. I do the same thing. By the way, mathematicians, when they write in first person, it's always we, not I. So when you're doing something when you're writing a math paper, you never say I did this. It's a we show this or we show this. It's because you're, again, leading the reader through the process. So we are doing it, not I am doing it. So Or perhaps it's the royal we. But but anyway, it's always a we. It's never an I. So if you ever look at abstracts for conferences where people are talking, it's always we in this talk we do this. It's never in this talk I do this, which is different from other disciplines. Other disciplines will use I, but in math it's always a we. It's how it's done for ages. Anyway, all right. So this notation just means we're going to suppose the first statement. We're going to suppose that W is a subspace of V. This is the shorter proof, by the way. That one's not too long either. But we're going to suppose that W is a subspace. Now remember, we talked about what the definition of subspace is before, right? Subspace means that W is a vector space, right? What do you know about when I said this before? When we say the words something is a vector space, there's a lot of information, right? What did I tell you that information was? If I say something is a vector space, what do you know about the set? It's not empty. It's not empty. You've got two operations and the 10 axioms are satisfied, right? What are two of the 10 axioms? Closure. That's the end of the proof for this direction, right? So W is closed under addition and scalar multiplication. Okay. That's it. That was the whole proof for that direction. It's just by definition. If I say it's a vector space, then it already satisfies those things. Okay. So let's go the other direction, which has a little bit more meat, but we've already talked through it. So when I'm going the other direction, assuming the second statement and proving the first statement, I use that arrow pointing to the left. It's just telling me I'm assuming the second and going to the first. It's just that it's a common notation that mathematicians will write. So in this case, we'll suppose that W is closed under addition and scalar multiplication. Now we need to show that it is a vector space. That's the whole point, right? I need to show that it is a vector space. Well, again, like I mentioned before, since W is a subset of V, we know that axioms 2, 3, and 7 through 10 are satisfied because these axioms are satisfied by all vectors in V. Okay. Again, the idea here is that everything in W is also in V, right? And we already are assuming that V is a vector space. And so again, just to reiterate, being a vector space tells you lots of information, right? In particular, the 10 axioms are satisfied. I don't need to worry about 2, 3, and 7 through 10 because it's not saying anything about special vectors. It says U plus V equals V plus U for all vectors in V. Well, then U plus V equals V plus U for all vectors in W because vectors in W are vectors of V. Right? Likewise, for axiom 3, it says U plus the quantity V plus W equals the quantity U plus V plus W works for all vectors of V. Well, it works for all vectors of W because it works for all vectors of V, right? Right. Notice there's not anything about any special vector in there. It says it has to be for all vectors, right? Which two axioms talk about special vectors? Those two axioms are the zero vector axiom, axiom 4, and additive inverse vectors, axiom 5. Those are special vectors, right? So remember what the axioms say. I'm going to write them off to the side so I don't stick it in the proof. But remember that axiom 4 says there exists a zero vector in V such that V plus 0 equals V equals 0 plus V, right? That's what axiom 4 says, doesn't it? The important part is that it says there exists 0 in V, right? We need to change this to, we need a zero vector in W, right? Well, if I know that W, without knowing extra conditions, if I know that W is a subset of V, do I know that a specific vector in V is also in W? Does it work the other way around? No, right? V is bigger, right? I know that everything in W is in V, but I don't know vice versa, right? So just because I know that this vector exists in V doesn't tell me it's automatically in W. And that's where the closure part comes in, right? Okay. So we know that V has a zero vector. Oops. We know that V has a zero vector, right? And if W is in W, we also know that if I take the number 0 times the W, I get this zero vector. And again, I'm going to emphasize that that zero vector is in V, right? I don't know it's in W yet. I know it's in V. Okay. Now, why do I know this? So go through it. I know I'm taking a long time to go through it, but there's concepts in here. Make sure that we're all on the same page with. V has a zero vector because I already am assuming that V is a vector space, right? So I get that, okay? W is in, if I take any little w and capital W, I know automatically that little w is also in V because I have a subset, right? Okay? And we already proved that if I take a vector in V and multiply it by the scalar 0, I get the zero vector in V, right? These are already things that we already know. Okay. Now, here's where we get the zero vector to also be in W. It's the closure part, right? Since W is closed under scalar multiplication, we have that the zero vector in V is actually in W. And now we have a zero vector. So axiom 4 is satisfied. Okay? I know I'm making a big deal out of it, but the idea here is that pardon me. The idea here is that just because I know that a zero vector exists in capital V does not guarantee me that the zero vector is in the W. Okay. Going back to the plane example, I said that the plane needed to go through the origin in order for it to be a subspace. Notice that if the plane misses the origin, I don't get the zero vector anymore. So it's not a subspace. Okay. In order for a plane to be a subspace, it has to go through the zero vector. To illustrate what I mean a little bit better, maybe, if for those of you who have had Calc 3, do you remember writing the equation of a line? Something like that in parametric form? Okay. So if I leave off the first part, the V naught, does that go through the origin? Can I get 0, 0, 0 by plugging something in for t? Yeah, just plug in what for t? 0. Ta-da, good. All right, so this would be the part of your line that actually goes through the origin. That part's a subspace. That shifts it off the origin. Okay. Notice that kind of fits that particular solution plus homogeneous solution. Same concept. Exact same concept. Just phrased in a different way. Okay. All right, so again, lines in space are not subspaces unless they go through the origin, but you can describe them as a shift of a subspace out of the origin. Right? It's been shifted off the origin. Okay. And you can do the same thing in 2 dimensions as well. But anyway, I just wanted to mention that. All right. Yes. Say that again. I know that in V, if I take 0 times any vector in V, I get the 0 vector, right? The 0 vector of V. W is a subset of V, so that's a vector of V. This is a subset of V, right? So if I take the number 0 and multiply it by any vector of V, I get the 0 vector in V. That's one of the properties you've already proved. Because I need to make sure, because I only know that I'm trying to show that W is a vector space, right? So I need to show that that W has a 0 vector. I know that W is closed under V, or under the operation, under the scalar multiplication. So the only thing I can show to get this to be in W, I need to take 0 times something in W to be able to use closure. That's why I had to use a little w and not a v. And I'm going to do it again here in a minute. Okay. So now let little w be in capital W. I need to show its additive inverses in there as well, right? Since little w is also in V, we know that, the additive inverse of W lives in V for certain, right? Again, we know that vector spaces have all of those properties satisfied, right? Okay. Including the additive inverse. So if I start with something in W, it's also in V. So I know its additive inverse exists, but do I know that it's in W yet? No, I know it's in V, right? And this is where closure is going to come in again, right? We know that -1 times this is the additive inverse, right? We already proved that for any vector space, correct? Right? Okay. And since W is closed under scalar multiplication again, we have that negative W is back in W again. So then we have that axiom 5 holds. Or not 5. No, it's 5. Axiom 5 holds. 1 and 6 are the closure axioms, which we're already assuming is a hold. So finally, we can say W is a subspace of V. Okay. So that puts your proof all in the same place. It verifies that we really can just check the 2 closure axioms. All right. So let's see if we can do another example or two. before we stop. Okay. Let's look at the next example. Must not take too long to prove it. It didn't leave you much space, right? Must not take too long to prove it. So vector space is R2. W is the set of everything that has a 0 y coordinate. Graphically, what is that? Which specific line is it? It's the x-axis, right? The y is 0. It's the x-axis, right? So I'm just saying here that what we're going to show is the x-axis is a subspace, basically, right? Okay. Okay. So again, let's let W1 equal, I'll call it x1 comma 0. I already know what the second component looks like, right? It's a 0. And W2 be x2 comma 0. We need to show that it's closed under addition and closed under scalar multiplication. So under addition, let's just add them. What is W1 plus W2 equal to? Yeah, just add the first components together, the second components, and when you add them together, you get 0. Does that have the correct form? Yeah. The form just says it can be any real number, but the second component has to be 0. So this is back in W. Let's take a scalar. What do you get when you take your scalar times a vector? Cx1, I'm worried about parenthesis and mistook it for my C. Cx1 comma 0. Does that have the right form? Yeah, so that's back in W. So the first statement, this statement right here, or this two statements, I guess I should say. What did we prove there? Closure under addition. This one proves closure under scalar multiplication, right? So we're done. Right? Unfortunately, I don't know why, but unfortunately, subspace doesn't have a fancy notation like many other things in math do. So that's why we're always writing is a subspace of. We have fancy notations for subset, obviously. There's also things called subgroups later on in algebra, abstract algebra, but no subspace notation. All right, let's look at the next. Yes. Say it again. This part is closure under addition. This part is closure under scalar multiplication. Yep. Okay. All right. Let's look at the next one. 4x4 matrices. We're going to look at the ones that are symmetric. Does that form a subspace? Same idea. We're going to test our two closure axioms. I'm just going to label them to start with addition and scalar multiplication. What letters do you want to use for the matrices in W? A, sure. Good. Let's let A and B be in W. What's the defining characteristic for being in W? It's symmetric, right? Well, that's interesting. I wrote an A and then M is symmetric. Yeah, that's a typo. It should be an A here. Sorry. It doesn't count as a mistake in class, by the way. That was out of class that I made that mistake. All right. What's the defining characteristic is that the matrix is symmetric. What is the definition of symmetric? What does it mean to be symmetric? Okay, so the dimensions have to be the same, and then what did you say, Kevin? Okay, so it's about the transpose, right? Then what do we say about A transpose? What is it equal to? A and, yep, B transpose is B, right? That's the product of the transpose of a product is the product of the transposes in the reverse order. The dimensions have to be the same. And if it's going to be symmetric, it has to have the same dimensions, right? The rows and columns have to be the same. Yep. What do we do with A and B then? What do we need to do with them? Add them, right? What do we need to show about the sum? That it's symmetric. To show that it's symmetric, what do you need to do to the sum? Take the transpose, right? Take the transpose. So now, if I take the transpose of the sum, what can you do with the transpose? Yeah, basically distribute it, right? But what is A transpose? A. What is B transpose? B. So A plus B is symmetric. So that's how we prove something is symmetric, right? Show that it's its own transpose. And that means the sum is back in W. Is that what we wanted to prove? Is that what we wanted? Yeah, cool. All right, so that's closed under addition. We did the addition part. How about scalar multiplication? Let's do C, B, and R, and I'll just use the same A, but I'll just rewrite it. Again, I need to show that C times A is symmetric. So I want to do C times A transpose. What can you do with the C? Just pull it out, right? The C doesn't do anything with respect to the transpose, really, right? And then A transpose is A. So C times A is symmetric. And it's back in W. So did we show that it was closed under addition and scalar multiplication? Yep. What's it? Not for we only remember scalar multiplication is just scalar times one thing, right? So I don't need to worry about the B. Yep. Hence W is a subspace of M44. Questions on that one at all? How about this next one? What do you think? What's the defining characteristic for being in W in this case?
Be first differentiated.
Yeah, when you take the derivative and you put in 0, you get out 1, right? Now remember, we're trying to show closure under addition or closure under scalar multiplication. If I add two functions, and I know the derivative is 1 at 0, what's going to be the derivative at 0 for the sum? I know that f prime of 0 is 1 and g prime of 0 is 1. What's the sum, derivative of the sum going to be at 0? 2. Is it back in there again? No. So is it closed under addition? No. So is it a subspace? No. Okay. So to write that down, let's let f and g be in W. Then f prime of 0 is 1, and so is g prime of 0. However, f plus g prime at 0 by our derivative rules is f prime of 0 plus g prime of 0. Just 2, and not 1. Not today. Take a different class, 2 might be equal to 1, but not today. Okay. I'm not joking. It could be a different class, 2 could be 1. That happens. It's okay. All right. So is this closed under addition? No. So f plus g is not in W. What does that tell you about W then? Is it a subspace? No. I don't even need to check scalar multiplication, by the way. Remember the notation too, just real quick. The C stands for continuity. The 1 says that the first derivative is continuous, and then this would be the interval on which it's continuous. So this is the set of functions that are one-time differentiable everywhere. That's what that means. Anyway, we'll do a couple more examples of subspaces next time, and then we'll talk about how we might generate subsets from subspaces, generally speaking. So we'll do that on Monday. Have a good weekend. We'll see you Monday.